All right. Today we are talking about conditional probability. We're going to define it here, but let me go through some of these new words. A frequency table is a table where my data is given. So this right here is a frequency table, and it's organized nicely with, sometimes they'll have like grand totals in the corners. You'll see that. Independent events, two events that occur separately from each other without, like one can happen without the other happening. Conditional probability, is a dependent event. Dependent events means that one thing can't happen without the other, and that's part of the conditional probability. So they occur, a dependent event. Two events occur and one affects the other. So it could be, if I ditch school, then I get in trouble. So I won't get in trouble, assuming I'm great otherwise. I won't get in trouble unless I ditch school. So one thing happens, I ditch school. And because I ditch school, I get in trouble. So they're dependent. One affects the other. And that is our big focus today, where for conditional probability, the probability that B will occur, given that A has already occurred. So this right now, A has already occurred. This is my prior event. It happened first. A occurs first. And then B happens. That's called a conditional probability. And in notes, it's actually written like this. So what's the probability of B happening? Let me write it in words. The probability of B happening given that A already occurred. The probability of B happening given A already occurred. So as we've written out every single probability, again, with this one, it's going to be the intersection, means the union, both of them, both A and B happening, divided by the outcomes of event A, the total. This is always, like usually the total, right? So we're going to be talking about all different scenarios, but for the symbols for the formula, probability of B and A happening together, both of them happening, and the probability of just A. Remember, A has to happen first. This is my prior. So A is this something that happened first. I ditched school, then I got in trouble. Things like that. I'm going to do, guess I'm ready to do example 1. I'm going to need the space underneath it. So I'm going to scroll down and have example 1 be on the forefront of the paper. Let's keep the formula up there. There we go. So read the paragraph question to yourself. The tables show the number of endangered and threatened animal species in the United States as of November 30th, 98. Find the probability that a listed animal is a reptile. So I'm really caring about reptiles. The listed animal, and I'm going to do is a reptile, R. And second part, the probability that the endangered, let's call that E, animal is a reptile. So listed animals are going to end up being like my total. I'll call them like A for total animals. So now I'm going to do some adding. So on your calculators, what's 59 plus 7? Let's do endangered first. 59 plus 75 plus 14 plus 9 plus 198.
$355.
355 endangered animals. Now let's do threatened. 8 plus 15 plus 21 plus 7 plus 69. Yeah,
120.
120. Okay. So grand total, if I care about all the animals, 475, right? So I'm going to do part A and part B, and I'm using this information up here, but A and B won't be. I'm going to use like E or R or A. So here's my first one. Part A of my question. The probability that a listed animal, A, is reptile. First, I have to have an animal, then it's a reptile. The ordering is, in order for it to be a reptile, it has to be a listed animal. First, I have listed animals. This is my prior event. Then I say, well, what about, is it a reptile? So that's good. That's good. So easy. Of all of the listed animals, how many are reptiles? That's what it's asking me. Out of the reptiles, what are they? Remember how it's desired? I want a reptile over total. I want to know all the animals. How many reptiles, Adam? 35. Total. All these animals listed. These are all listed. Total. Grand total. Divided by 475. So then I divide that and I'm going to get a decimal. In my probability, I want decimal answers. So what's the decimal answer? Someone on Zoom, we'll go back and forth.
7.37%.
Too high. Well, I don't want the percent. Can you give me the decimal first? I mean, I want decimal answer.
0.073.
Yep.
Where did the 35 come from?
Oh, reptiles. 14 plus 21. Thank you. And if you round more, it might be 0.074. It's fine. All right, now, part A is done. It's simply that. That's it. Part B, the probability that an endangered animal is a reptile. I just am focusing on endangered now. So first I have to have an endangered species, and then I'm like, well, is it a reptile? So the ordering is, first I have to have an endangered animal. Then, because this is my prior event, remember how the prior event is the second one? Then, well, is that endangered animal a reptile? So here's what I care about now. I want it to be endangered reptile. How many of those are there? That's my numerator. Just an endangered reptile is how many reptiles total?
14.
14. Total endangered. Total endangered. 59, 75, 14, 9, 198. So let's divide that. 14 divided by 355. You'll have calculators. Everyone at home has a calculator. Should be quick. Colin, what'd you get? I'm calling on Colin. When you divide it.
0.039.
Okay, let's round it. So 0.04, just since I have my hundredths place, is fine. Great, that's it. So we're good. We're gonna go on to the next example. Diego? Diego wonders whether the amount of sleep he gets is related to the amount of coffee he drinks. So it is true that some people are not affected by drinking coffee, but some people would be affected by drinking coffee at night versus the morning. And then how many cups? There's all sorts of things we can talk about. But some people are, like if they drink coffee in the evening, oh, sleep is not happening. So Diego wonders whether the amount of sleep he gets is related to the amount of coffee he drinks. For 10 weeks, he records how many cups of coffee he drinks each morning. So he's not drinking it at night, he's drinking in the morning. And how many hours of sleep he sleeps that night, rounded to the nearest hour. Okay, just a little explanation. Here's a frequency table. 4 times in the 10-week period, he drank no coffee in the morning and he got 6 hours of sleep. 12 times during this 10-week period, he drank no coffee and got 8 hours of sleep. 7 times he had 2 cups of coffee in the morning and got 7 hours of sleep. So that's how you describe the graph. 6 hours of sleep happened for him 27 times. 7 hours of sleep happened 22 times. 8 hours of sleep happened 23 times. 2 cups of coffee, 24 days, he had only 2. 26 days, he had only 1. 22 days, he had no coffee. So everyone's good on that. Based on the data, I want to know, and this is going to be my formula from up above, ready? The probability of A and B divided by the probability, and this one's going to be B because B, A, my cups versus my hours, okay? Cups versus hours. You have to actually drink coffee or not drink coffee in order to get the sleep. So that has to happen first. I mean, that's common sense, right? So I'm going to do this right here. So I want to know the fraction. This probability is going to be how many 8 hours and 0 cups. That's going to be my numerator. How many? 8 hours, 0 cup. How many times did that occur on your chart? Easy, right? You just look at the number. 12 times. Then the denominator is going to end up being the total 0 cups days. The total 0 cup days. Zero cup total 22. So he drank no coffee and he got 8 hours of sleep that night. Divide. Someone here in class. Yep. Good. So it's this as a decimal, and it says to the nearest percent, round to the nearest percent. round your answer to the nearest percent. Okay. Here we go. I'm moving on. We have 2 more examples to do. I'm teaching you another little concept, something about independent and dependent. So let's discuss that. Okay. If events A and B are independent, separate of each other, then the conditional probability of B given A, the probability of B given A equals the probability of B. So notice how the first letter, the probability of B given A happens is going to be equal to the probability of B. That's if they're independent. So that's 2 sentences starting there. And then second portion, flipped, converse. The conditional probability of A given B happens equals the probability of A. So I want the probability of B happening given that A already happened needs to equal the probability of B. That's if it's going to be independent. Both must be true for the events to be independent. And when I say true, I mean their probabilities must be equal, the same probability. This here basically sums it up again. And if the probability of B given A equals B, yeah. And the probability of A given B happening equals A, once again, I'm going to put stars because the first number in my parentheses has to equal that same alphabet letter. Then they're independent. This is what I wrote. This is the same thing. If one of them is false, if the probabilities would equal each other, then the events are dependent. This is asking us, are the events independent or dependent? That's what we're going to be asked. Are the events independent or dependent? All right, I'm moving. We're going to talk about students taking French at school. The table shows the juniors, all the juniors at school. So there are 45 girls take French, 255 girls don't take French. There's total in the junior class, 300 girls. There are 30 boys that take French. There are 170 that don't take French. There's a total of 200 boys in the junior class. Together, all the kids, all the juniors is 500. The French students, there's 75 juniors, boys and girls that take French. There's 425 boys and girls that don't take French. A student from the junior class is selected at random. Let G be the student as a girl, put a G above it. And let F be the student who's taking French. I need to represent both. Remember up above how I had the converse, I had 2 parentheses. I need to find out 2 things. What's the probability of it being a girl given they're taking French? It being a girl given they're taking French. And remember how it has to equal the first letter in the parentheses? I want to know, does it equal the probability of it being a girl? Or probability of girls? All the girls. I also need to do flipped the probability of a kid in French given all that it's a girl. So these are opposites of each other. And then the first letter in the parentheses, the probability of just French in general. I want to know if these are equal to each other. If both are true, if this probability equals this, does this equal this? Because if you look up above, that's what it's asking. These need to be equal. So let's do it. The probability of it being a girl, given that they're French. So I'm going to do girls, French on my numerator, and I'm going to do total French on my denominator. This is the girls that take French. So I look on my chart, frequency table. The girls that take French, there's 45 of them. They're in the numerator. The total French in the juniors, 75. What's that decimal division? Or just oh yeah, go ahead. 0.6. 0.6. Great. I want these to be equal. I want these fractions to be equal. The second fraction says just the girls and then the total juniors, G. Just the girls, 300, and the total juniors. 300 divided by 500. Divide that. Someone on Zoom, tell me.
Point six.
0.6. Yay, they're equal. So far, so good. These are independent because they are both true. They're both the same probability. Now I'm flipping it. And I'm doing the girls in French divided by my girl total. Girls in French, 45. Girl total. Uh, 300, right? Write it out, write it down. What's the answer? Yes.
0.15.
Good. Well, let's see. Now I'm just doing French, the probability of just French. That's going to be my French total over the whole school, or no, the juniors, all juniors. Okay. French total and all juniors. French total, 75. So I'm not caring about male, female right now. All juniors total, 500. Is this the same decimal? 75 divided by 500. It is. We're simply dividing in our calculators. Okay, since this is true, they're both true, independent. So the question says, are events G and F independent or dependent? They're independent. Events G and F are independent. Cool. Last example. Parking lots, cars in a parking lot. Great. Okay. A vehicle in the garage is going to be selected at random. Let B represent that the vehicle is black. Let V represent that the vehicle is a van. B and V. Great. Are they independent or dependent? So I'm doing the same thing as I did the problem above. I need to find the probability of B given A, or B given V, and V given B. So remember how this, this must be equal to the probability of just B, the first letter. Then I'm going to switch it. First letter. Let me tell you what it looks like. Black. So, given a vehicle is black, but first it was a van black van, right? Black vans, vans, no red, no white, all black. 3 out of 3. Black van out of the total, 3 out of 3, that's great. Black van, total vans, in case you want to know how I'm getting what I'm getting. It's 1. Followed by just the probability of black. Just the probability of black total. Black. And then I'm going to do total cars. Well, black cars consist of 13, right? 13 of them. Here it is on your chart. 13 of them are black, the cars. Like total. Out of total, like everything in the parking garage, everything. 22. Are these the same? Because if they're the same, then we're on our way for it to be independent. We have to check this too. But well, 13 divided by 22 is not 1. So this right here, I already know this is not independent. Because if this is not true, I don't even have to do the work on this one. If this is not true, then they're dependent. Events B and V are dependent. One of them is not matching the other. The proportions, the probabilities are not the same. Last example, let R represent selecting a red vehicle and C represent it being a car. Only red, only cars. Red car, I got 5. I'm gonna have to talk about 11, probably the total. Let's see how it goes. Here's what you write. The probability of it being a car first and then it being red. And the first letter in my, then I'll do my red. I also have to do the converse. It being red and then it being a car. And the first letter in my probability of just the cars. So I have to do both. Start the first one. I want a red car over total cars. Red, there's 5 of them. Over total cars, that's this 11 down here. Okay. Then I want to know just the probability of red. So this is going to be red cars, red, everything. What's red? Everything over the total. Red total over the car total. Red, cars, vans, and pickups total. Do you see how it's 7? 5 plus 7. I'm sorry, 5 plus 2 makes the 7 red. Hoping you think this is easy. Cars total, lower right-hand corner of my frequency table, 22. Do these equal each other? Because then we're on our way for it to be an independent event as soon as I check the other. You should see that the probabilities don't match up. $5.11, 7:20 seconds. No, they're not the same. What are the decimals? I want to write down the decimals. Someone tell me.
So 5 divided by 11 is 0.45, and then 7 divided by 22 is 0.31.
Okay, so, or 32, okay. The point is they're not the same. So, events R and C are dependent. Okay, yep. Okay. All right, so we're gonna stop there for notes today. Let me stop the recording.